In this video, we'll take a look at inverse functions, and we'll start with an application that you're probably familiar with. So if you ever had to convert between temperatures measured in Fahrenheit and temperatures measured in Celsius, there's a formula. The formula is C is equal to 5/9 times F minus 32. So if you want to convert 75 degrees Fahrenheit to Celsius, we would take our value for F and substitute it in the formula. So we get 5/9 times 75 minus 32. We open the calculator, we get 5 divided by 9 times parentheses 75 minus 32, and we end up with about 23.9 degrees. So what if you want to convert the other direction? So let's say you have degrees measured in Celsius and want to convert to Fahrenheit. If you want to convert 21 degrees to Celsius to Fahrenheit, you could certainly use the same formula, except now you'd substitute 21 in for C and solve for F. So if we had to do this many times, we would multiply both sides by 9/5. So I would get 21 9/5 times 21, multiply both sides by 9/5. These cancel, and I would have 9/5 times 21 is equal to F minus 32, then add 32 to both sides. And if I only needed to convert one temperature, that would be fine to go ahead and do this work. But what if I want a formula that allows me to convert? So what we can do then is take this formula and solve the formula for F. We would end up with 9/5 times C is equal to F minus 32. Add 32 to both sides. F is equal to 9/5 times C plus 32. So if I wanted to then convert 21 degrees, what I could do is just substitute it in this formula. So I would get 9/5 times 21 plus 32. The result is the same, but the formula ends up being what we call an inverse. It's the inverse operation. So let me go ahead and finish our conversion so we can get an answer here. So if I take 9/5 times 21 and then add 32, I end up with 69.8 degrees. So the two formulas, finding Fahrenheit or Celsius given Fahrenheit and finding Fahrenheit given Celsius, these two are considered inverses of each other. They're inverse operations. So what is an inverse? So in non-technical terms, given a function, the inverse results when we switch the domain, the inputs, and the range, the outputs. We take x and y, basically, and switch. There's a notation for inverse. The inverse of a function f of x has the notation f inverse of x. So if you think about the formula above, if my original function was the first equation, 5/9 times x minus 32, I'm writing my function conversion in terms of x and f of x, then the inverse would be 9/5 c plus 32. These are inverse operations of each other, inverse functions of each other. And the notation, f with a -1, means inverse, not to the power of -1. And just a note, a function has an inverse only if it's 1-to-1. So remember from a previous section, 1-to-1 means your function is a function because it passes the vertical line test, but it's also 1-to-1 because it passes the horizontal line test. So we can have functions that have inverses given to us in a variety of ways. So one way is a table of values. So this function, f of t given below, shows distance in miles that a car has traveled in t minutes. So t, 30, 50, 70, 90, and f of t are miles. If you wanted the inverse of that, then you would interchange the miles and the minutes. So instead of having a coordinate 30, 20, you would have the coordinate 20, 30. You would interchange your x and y's. So when we're finding and interpreting, find and interpret f inverse of 70, f inverse means I'm given the y coordinate and I want to find the x coordinate that goes with it, or the t coordinate. So for your function f of t, all of the coordinates are given t minutes, f of t miles. All of your coordinates in the inverse are given miles and then minutes. So when you're interpreting f inverse of 70, you're given 70 miles and want to know the minutes that go with. So it takes 90 minutes. So the inverse of 70 is 90. When you're given a graph, the same idea. We're going to take a look at this particular graph and do 3 different things to it. We're going to find f of 1, which is just your regular function notation, f of 1. That means when x is 1, what is the y coordinate? So when x is 1, the y coordinate is 0. So f of 1 is equal to 0. That would mean that f inverse of 0 is equal to 1. So if you have a coordinate 1, 0 on your function, then the inverse is 0, 1. So if we want to find f inverse of 2, then that means we're given the y coordinate. And we want the x coordinate that goes with it, f inverse of 2. So if we're given the y coordinate of 2, so you know that f of 2 is equal to 1, but where the y coordinate is 2 is here at x equals 4. So if f of 4 is equal to 2, then f inverse of 2 is equal to 4. So you interchange the points. So taking a look at the graph, notice that the graph is 1 to 1. It's a function because it passes vertical line test, and it's also 1 to 1 because it passes the horizontal line test. The domain of our function, in this picture, only the positive x values are used. This arrow means it's not going to cross the x-axis or the y-axis. So the domain does not include x, 0 to infinity. So the domain is all positive values of x. The range on the y values is all real numbers. Okay? So I want to graph the inverse on the same coordinate axis. So how would I do that? I'm just going to sketch. I'm going to take my coordinates. Here I have a coordinate when x is 1, y is 0. So I'm going to switch. I had the 1, 0. I'm going to switch. 0, 1 is a point on the inverse. I have a point 2, 4, 2 on my function. So the point 2, 4 is on the inverse. And if I keep taking points, coordinates, this looks like it's 1, about negative, or 1/2 negative 1. If I go negative 1, 1/2, and I connect, then what I end up with is a sketch of the inverse. So notice, for every coordinate x, y on this function, there's a coordinate yx on this function. So what happens is, it ends up being reflection of each other. There's a symmetry line. The symmetry line is the identity function y equals x. So when you have a graph of an inverse, a function, and its inverse, they're reflections of each other over the line y equals x. How come? Because we basically take the x and y coordinates and switch. And then when you identify the domain and range of the inverse, the domain and range of your original function switch. So the domain of the inverse is whatever the range of the original function was. The domain is negative infinity to infinity, and the range now is from 0 to infinity. Okay, so we've taken a look at a table of values, and we've taken a look at sketching graphs of functions and identifying domains and ranges. Let's take a look at equations. How do we find the inverse of a function in equation form? So we have the function f of x is equal to x to the third minus 2. Then we're going to graph both the function and the inverse on the same axis, just to show the reflections of each other. So when you're finding an inverse, the first step you do is let's substitute y for f of x. So instead of writing f of x equals x to the third minus 2, I'm going to write y is equal to x to the third minus 2. Step 2, interchange x and y, or switch x and y. So instead of y equals x to the third minus 2, I'm going to get x is equal to y to the third minus 2. Then solve for y. So I'd add 2 to both sides. I end up with x plus 2 is equal to y to the third. Take the cube root of each side. Y is equal to the cube root of x plus 2. When you get to the end, when you found the inverse, then substitute back in the right notation. Let y equal inverse. So the inverse is the cube root of x plus 2. So that's just like taking your variable and solving your equation for x, except now we're calling them inverses. So if my original function is x to the third minus 2, then the inverse is equal to the cube root of x plus 2. And just to make sure, let's graph those on Desmos. I'll use y equals. So our first function was y is equal to x to the third. What was it, minus 2? Let me double check real quick. Yeah, x to the third minus 2. And the inverse was the cube root. So we need the keypad. Cube root and to the power of a third are the same. So if you don't want to go through and look at all the functions to try to find the cube root, I'm going to take x to, here it is, cube root of x plus 2. So when you take a look at these two graphs, notice if I were to put in the graph of the line y equals x, my two functions, the function and the inverse, are reflections of each other over that line. So that's one way you can check and make sure that your equations are correct. All right, next example. Find the inverse of the function x squared plus 1 if x is greater than or equal to 0. And then graph them both in the same rectangular coordinate system. Well, on here, f of x equals x squared plus 1, just a reminder, that's the graph of a quadratic moved up 1. It's the graph of x squared, one of our toolkit functions, moved up 1. But notice this is not a one-to-one function. It is a function, but it fails the horizontal line test. But we can restrict the domain at x is greater than 0. And that way, we end up with a one-to-one function. So if it's not a one-to-one function, you can restrict the domain. So if our function is y equals x squared plus 1, and I want to find the inverse, switch x and y, x equals y squared plus 1, and then solve for y. Subtract 1 from each side, I get y squared equals x minus 1. Square root both sides, I get y is equal to plus or minus the square root of x minus 1. This has two pieces to the function. There's only one of those that makes sense. We have to restrict the domain. So here, if the domain is x is greater than or equal to 0. Notice the range ended up being from 1 to infinity. The domain is from 0 to infinity. So when I restrict and switch in the inverse, then the range becomes 1 to infinity, or the domain is the range of my other function, and the range is the domain of my original function. So I'm going to end up not using this piece. My inverse is going to be just the positive square root of x minus 1. And the inverse would look like the square root of x function moved to the right one. So here's my function, f of x, and here's f inverse of x. And they are reflections of each other across the line y equals x. All right, next example is, I just want to do an example of a rational function just to get you to take a look and remind you some of the algebra that goes with rational functions. So if this is our function, y is equal to negative x plus 3 over 2x minus 2, and we want to find the inverse, switch your x and y coordinates. X is equal to negative y plus 3 over 2y minus 2. Notice this is going to be a little more complicated to solve for y. So the first step is multiply both sides by 2y minus 2. I get x times 2y minus 2 is equal to negative y plus 3. Multiply out on the left side, multiply through by x. I get 2xy minus 2x equals negative y plus 3. Now I'm trying to solve for y, so get all the terms with y in them on one side and all of your other terms on the other. So I'm going to end up with 2xy minus y on the left-hand side is equal to 2x plus 3 on the right-hand side. So how you solve for y when you have it in multiple terms? Get all the terms on one side that have the variable you're solving for, and then factor out a y. I'm left with 2x minus 1 equals 2x plus 3. Divide both sides by 2x minus 1. And then interchange, put in your notation. So the inverse is 2x plus 3 over 2x minus 1. All right, so to summarize, in mathematical terms, general notes about inverse functions. For any one-to-one function, f of x equals y, the inverse, f negative 1x, inverse function, if f of y equals x, that means interchange x and y. So this piece right here has to do with compositions of functions. So a function in its inverse, this is the only time, if you remember when we did compositions of functions, in general, when you take compositions of functions both directions, you don't get exactly the same answer. But if the two functions are inverses of each other, then the composition of functions either direction will be the same, and they will both equal x. So for example, one of our functions that we did today was x squared plus 1, and the inverse was the square root of x minus 1. Let me just double check. I want to do the last one that we did up here. So our function was x squared plus 1, inverse was square root of x minus 1. When you take the composition of functions, f composed with the inverse, we get the square root of x minus 1 squared plus 1. The square root of anything squared would be x minus 1 plus 1, which is x. So the composition of functions in this direction is x. Then check the other direction. f inverse composed with f of x. If you take the square root of x minus 1 and substitute what your function is, x squared plus 1 for x minus 1, you end up with the square root of x squared, which is x. So if functions are inverses of each other, then the compositions will be equal, and the composition of functions, both directions, is equal to x.